Okay, great. So thanks for the invitation to give a talk at the conference and also to lecture at this very diverse summer school and have the opportunity to interact with students from particularly diverse backgrounds. So what I want to give a talk today is a pretty broad overview of what's going on in dark matter direct detection and where I think the future is going to be over the next 10 years. So let me start by, I've titled the talk Beyond the WIMP. And so you might want to ask the question, well, what's wrong with the WIMP? Why are we looking beyond the WIMP? And to do that, I think we need to spend some time looking at where our experimental status currently is. So this is, I think, probably the most, by far, useful plot to have come out of the SNOMAS process. And it gives us a summary of where the direct detection experiments are at. So here's a plot of the dark matter scattering cross-section off of a nucleus as a function of the dark matter mass. And you can see this huge diversity of experiments pushing down in cross-section. You can see that they cover the dark matter mass range above about 10 GeV. And the solid lines are the current constraints. So they're going down to the level of about 10 to the minus 45 centimeters squared. I'll tell you why that's significant in just a minute. And you can see also this neutrino background. So that sits around 10 to the minus 48 centimeters squared for weak scale cross-section. And to just parse this in terms of the most important physics on this plot, people talk about the fact that we're looking for the weakly interacting massive particle. And strictly speaking, that's not really true. And the reason why that's not really true is that weak interactions, namely scattering through the Higgs boson, has already been ruled out. So that scattering cross-section is on the order of 10 to the minus 39 centimeters squared. And that's now ruled out by something like 5 to 6 orders of magnitude. What we're actually probing right now, and what is symbolized here by this red blob, is scattering through the Higgs boson. And that benchmark is around the level of 10 to the minus 45 to 10 to the minus 46 centimeters squared. There are big errors on that for reasons I'll discuss in just a minute. And the other thing I wanted to draw your attention to is the fact that the sensitivity of these experiments really rapidly dies around 10 GeV. Now, the reason why Higgs scattering dark matter has such a smaller cross-section is effectively just the fact that the Higgs coupling to the nucleons is much smaller because you couple proportional to the mass. So the dominant contribution is going to be through a loop of top quarks. And so when you compute this for sort of typical cross-sections, so this is the down-type Higgsino fraction of the dark matter, if you put this in the context of the MSSM, for moderate tan beta, you can get very large cross-sections, but if you put in 125 GeV Higgs tan beta of 1, you can rapidly see why it is that we're focused on this region here of around 10 to the minus 45 centimeters squared. Now, that said, looking at this plot, you would infer that by the time that we get down to the neutrino background down here, we would have basically killed the neutralino within the MSSM. That's deceptive, though, and the reason why that is deceptive is because pure states within the MSSM do not couple to the Higgs boson. So if you just write down the Feynman diagrams for coupling to the Higgs boson, you need a mixture of Wino Higgsino or Bino Higgsino in order to actually get a coupling to the Higgs. If you have a pure Bino, a pure Wino, or a pure Higgsino, you just don't generate a scattering cross-section. So strictly speaking, you can have zero direct detection cross-section at tree level. Okay. Now, on the other hand, if you did have a pure state, a pure Wino or a pure Higgsino, for example, even if you wouldn't see it in direct detection, in a direct detection experiment, it could show